Good morning, class. In today's lecture, we will be discussing about the lines of electric field or force. Now, so far we have seen what is the formula for electric field or electric force, but so far we have not seen what electric field lines look like. Okay, so I would like to give you a brief idea about the positive charge and a negative charge. As you can see, I have made a positive charge here, and if you see different lines here, these lines originating from these are what we call as electric field lines. Okay, this is what we call as electric field lines. Now if you see both of the charges, this positive charge and the negative charge on this side, they both have lines, but the dissimilarity between these two lines are, see, one of them are going out of this charge and the other one are coming in. Okay, so what it means is the positive charge will have electric field lines which are generating towards the outside, and the negative charge has electric field lines which are terminating at that point charge. Okay, which are terminating, as in all these field lines are closing in towards the negative charge. Okay, so I have written this as well. The electric field lines generated from a electric field lines generate from a positive charge, which means they go out of that positive charge. The second one is electric field lines terminate at a negative charge, which means the electric field lines close in on the negative charge, which means all the lines that you see, they will be coming in towards the negative charge. And the third thing is, okay, the third point is number of field lines passing through a unit area at a distance decides electric field strength. Now if you look at this example, in this example, see what do you think, which kind of charge is it? The lines are going outwards. Is it a negative charge? No, it's not a negative charge, it's a positive charge. A positive charge is the one where the field lines are generating. Okay, generating towards the outside. Now look at this. The third point says, if I take a unit area, okay, anywhere, if I take it at a distance, I check a unit area and I see the number of field lines passing through that unit area, that number will decide what will be the electric field strength at that distance. Okay, now I have made two different points. Okay, point P2 and point P1. For now, let us look at this point P2. What do you see at point P2? And this is a unit charge, this is the unit area. So both of these areas are same. If I look at point P2, in this unit area, how many electric field lines do you see crossing this area? It is only 2. So right now let it be. If you look at point P1, okay, if I look at point P1, how many lines do you see are passing through this unit area at point P1? This is 1, 2, 3, 4, 5 and almost 6. So 6 electric field lines I see crossing through point P1, the unit area at point P1. So which means the electric field strength at point P1 is greater than that of point P2. Okay, the electric field strength will solely depend on the number of electric field lines passing through any given point at a certain distance. Okay, so this also implies the closer I come to this charge, the closer any charge particle comes towards this charge, the greater the electric field strength will be. Okay, the closer you come to this charge, be it the repelling force or the attracting force, the closer you come to this charge, the greater my electric field strength be. Okay, and the more you go away from this charge, the less electric field lines will be there. That means the less electric force will be there. Okay, which is quite intuitive. Any one can solve that one. If you move away from these electric field lines, if you move away from this Q charge, the electric force that you experience will be less, as soon as you get closer and closer and closer to this charge, the electric field strength will increase. That means the electric force will increase as soon as you approach towards this charge. Okay, so this is what I meant by this third line, which was number of field lines passing through a unit area at a distance decides its electric field strength. Okay, now let me give you another example. It's not an example, basically it's a concept. So electric field lines by like charge pair and unlike charge pair, what happens? So if you see a positive charge and a positive charge, lines go out. Okay, so these lines, if you look at these lines, they do not converge, they are diverging away from each other. Okay, why is it happening? Just because this pair is a like charge pair. These are positive charges. Okay, as soon as I come close and close and closer and closer and closer, if I move this charge particle toward this particles, this electric field lines will bend more and more away. Okay, if I bring it very close to each other, all of these lines will point to this direction, the other direction. From this point they will point to the other direction, the opposite direction. Okay, this is what happens in case of like charge particles. If I look, okay, look what I have written over there. This is a like charge pair. If I look at negative and if I look at this positive charge pair, the lines generating from the positive charge pair, okay, the positive charge pair and the negative charge pair, this, the one generating from this side is converging to the negative side, which means these lines are joining directly. If I move it closer to the negative charge, if I move this positive, these electric field lines will close up. Okay, as soon as it moves closer and closer and closer, all these electric field lines will join, and once it hits this negative charge, all these lines that you see will become a straight line, and the electric field or electric force will be of a very great magnitude once I bring it towards. Okay, in this case as well, if I had brought it towards this, the electric field lines would have been very stronger, but in the opposite direction, which means the force of repulsion was very great in this case. Here if I move it very closer, the force of attraction in this case will be very great. Okay, thank you so much. I'll catch up with you in another lecture. Okay, guys, before I directly jump to the topic electric potential energy, let me tell you something about integration and differentiation. Okay, and this is for those who do not know what integration and differentiation is about. Okay, I have some quantity x square. If I differentiate it with respect to x, it becomes how much? Let me write it as n. Okay, x to the power n. It becomes, after differentiation, this quantity will become n into x to the power n minus 1. Okay, and this value x to the power n, if I integrate it with respect to x, this quantity becomes x to the power n plus 1 divided by n plus 1. Okay, if you want me to give you an example, here is your example. Okay, x to the power n is, I'll write x square, I'll differentiate it, it should become n, that means 2, x to the power n minus 1 to 2 minus 1, which is, answer should be 2x. Okay, if I integrate this 2x, I should get back this answer. Okay, let me do this. Integration of 2x should give me, what did I tell you? It becomes x to the power n plus 1. What is the power of x? 1. 1 plus 1 is 2, and this 2 is already there, 2 divided by n plus 1. N plus 1, x to the power n is 1, 1 plus 1, which is 2. This 2 cancels out. I am again left with how much? X to the power 2. So this is how integration works. The formula is x to the power n d by dx. If I do this thing, it becomes how much? N x to the power n minus 1. If I integrate this value, or this value, if I integrate x to the power n with respect to x, it becomes how much? it becomes how much? X to the power n plus 1 over n plus 1. This is you have to keep in mind. So after this, if you're clear with this, I'll jump to your electric potential energy. Okay, let us look at the topic electric potential energy. Okay, in electric potential energy, I have a system of charges. You can see Q1 and Q2 are the charges. Now AB is the distance. I have written this distance as R1, and AC, do you see the point C? The point C, the distance AC I have written is as R2. Okay, and we looked at the integration. The reason why we looked at integration is because we are going to do it right now here in this topic, electric potential energy. Okay, so now the distance, the force between these two particles, the electromagnetic force between Q1 and Q2 will be given by F is equals to K Q1 Q2 over R square. R is the distance of separation between them. Okay, now if this charge, okay, I'll tell you, if this charge Q2, I move it a little, okay, if it moves a little distance, how much is it? Dr. If it moves a little distance Dr, that means a work is being done, a little work is being done. Okay, if you ignore this d, you can see work done is equals to force into displacement or distance. So if it moves a little distance, there will be a little work done. Okay, so what I'll do is I'll write this force into dr. This force is k q1 q2 over r square into dr. We'll do it as dr. All right, now look at this. To find out how much will be my total work done if in moving this charge through some distance will be, I integrate this dw. We saw the integration, right? I integrate this dw, and this would be this into dr. Now this dr over r square term, I will write it inside of this integrate sign. Okay, these constants are going to come out. What constants? K q1 and q2 will be outside, and now this, okay, 1 over r2. Look at this. If you remember this thing, if you remember 1 over r square is equals to r to the power minus 2, I can write it like this. Now I apply the formula of integration. R to the power minus 2 dr is equals to, I integrate this. This becomes r to the power n plus 1 over n plus 1. Okay, this becomes r to the power minus 1 over minus 1, which becomes minus 1 upon r. Okay, so after doing this integration, all I am left with is minus 1 over r, and the limit that I'm setting for this integration is from limit r1 to r2. Okay, so what I'll do is, if I ignore this negative sign, I could have written this as 1 over r2 minus 1 over r1, but there is a negative sign, so these will reverse. It will become 1 over r1 minus 1 over r2. Okay, so the electric potential energy, okay, the electric potential energy will be written as how much? This negative. This, see, one more thing, electric potential energy of a system, the change in electric potential energy of a system will always be the negative of work done. Okay, it will always be negative of work done. Why is it so? Because in order to make it r2 minus r1 form, I'll have to bring a negative out. It becomes this k q1 q2 1 over r2 minus r1. So the negative sign is written outwards. Okay, this form becomes this form only when I write a negative sign outside. So we write change in electric potential energy as UR, and change in potential energy means, if, look at this, if I move this, this is fixed, okay, this is fixed, we are not doing anything, this q1, we're only moving q2 from point B to C, okay, we are moving it from point B to C, and we calculated how much would this be, this, it, once we found out how much work is done in moving this much amount, so we'll find how much work will be done from moving it from point B to C, okay. And in this scenario, last scenario, we can write it as, you can write this as change in potential energy will be u r2 minus r1, r1 being your initial position where from where you started moving the charge, r2 is the position where you will keep the charge afterwards. The second thing is this u, that means the change in potential energy will be equal to negative of work done, and the negative of work done will be how much, this k q1 q2, and bracket there will be minus, oh sorry, 1 over r2 minus 1 over r1, okay. So just to tell you, if you look at this, if I'm bringing this charge, okay, if I'm bringing this charge, look at this charge, if I'm bringing this charge from a distance which is infinitely distant from q1, and if I'm bringing it to how much, if I'm bringing it to point B, if I'm bringing it to point B, which is r, with this I have written this as r, I can write it as r1 as well. So how much would that be, u r1 minus u of infinity, I'll write it as k q1 q2 bracket 1 over, I could have written r1, but I'm writing as just r for the sake of simplicity, 1 over r minus 1 over infinity, 1 over infinity is 0. So this will be my final value, k q1 q2 over r. K is how much, 1 over 4 pi epsilon naught, 1 over 4 pi epsilon naught. So what this value means is, this value means if I'm bringing a charge from infinity to a position which is at a distance r, how much work will be done, this much work will be done, okay, this much work will be done in bringing that point, bringing that charge from infinity to a point which is at r, which is a distance r from the fixed charge, okay, and that will be my change, that will be my change in potential energy, okay. All right, we'll look at some example about this after this session. Thank you so much. I hope this makes sense.